All right, ladies and gentlemen, we're going to explain how Le Chatelier's principle can be used to maximize the yield of our ester today. That's our goal, to make as much ester as possible. So Le Chatelier says if you add an ingredient to one of the sides of the equation, because the equation is in equilibrium, that means the ratio of the concentration of the products over the reactants is a constant called the equilibrium constant. So if you add like one of these chemicals, you still need to have a constant for K. So this would be in the denominator because it's products over reactants. And to compensate for making something bigger in the denominator, you're going to have to increase the numbers in the numerator too. What you guys learned was, you compensate by moving away from what you added. Shifting, we called it. It's a good principle. So if I add an excess of one of these chemicals, which we do in today's experiment, then that will help shift the equilibrium towards one of the products. So Le Chatelier improvement number 1, add an excess of one of the reactants. Now I want you to tell me which of the two chemicals is present in a large excess today. You need only look at the millimole amounts in your data table for isoamyl alcohol, and I need a number right now. Isoamyl alcohol is what? No, I want millimoles, please. 7.4 millimoles. Acetic acid is? Wow. It seems to me when the stoichiometry is 1:1 and you use a large excess of that one, acetic acid, let's see, 3 times 7 is what, 21? So it's a greater than 3-to-1 excess, right? And that should shift the equilibrium to make more ester. I got a sub question. Why did they choose acetic acid? They being Mayo, Pike, and Trumper, the authors of your book who designed the experiment. And does anybody have any suggestions why they picked that one? Try to think real life. Real life. Try to think big scale. Big scale. Try to think America. We got to make a profit. There's a clue. So remember, the excess chemical is the one you're going to have to throw away the excess at the end, right? So what do you think I was leading up to about why they chose acetic acid? It's the most abundant? That's what I liked what you said the first time too, because it was true. But she said it's cheaper. Answer, part I. It's much cheaper. And 2, for chemical reasons, I think 2 is more important than 1 in this particular case. What have we been doing all during experiment 4? We were proving only one thing in experiment 4. If you need to enhance the water solubility of, say, an acid, take its proton off, and then you can easily remove it from an organic layer. If you wanted to, in experiment 4C, enhance the water solubility of a base. Put a proton on it, make it an ion, it's water soluble. We're not doing that today because we're not dealing with bases today. But acetic acid is more easily removed, using aqueous base extraction. Remember, it's the excess. You're going to have to get it away from your ester. And a great way is to have an organic layer where your ester remains. You were going to use ether today as your solvent. And then add a base to the aqueous layer so that you can deprotonate the acetic acid and make it fully water soluble. And that'll be away from the organic layer, right? So, two good reasons. Easily removed during aqueous base extraction. Now, Le Chatelier says not only can you add excess chemicals to the left side to force it to go to the right, but you can remove one of the chemicals that are produced to force it to replace that chemical. Water in this reaction is easily removed using something very similar to sodium sulfate that we've been using to remove water all semester. Sodium sulfate was great because it made it precipitate with water, right? Sadly, under today's conditions where you're supposed to boil the reaction at 160 degrees or 180, something like that, the sodium sulfate cannot hold on to the water at that heat. The water just comes back off. No problem. Pick another anhydrous substance that makes a stronger hydrate with water. And it's the one found in so many things nowadays. Every time you buy something that's been sitting on a shelf for a while, they'll put a packet of this stuff in there. And it always says, do not eat on the packet. And it also says what's in the packet for those that are interested. What is that substance in those packets in your shoes or electronics when you buy them? Anybody? You were supposed to use it today. Silica gel beads. Silica gel beads make hydrates that can withstand the heat of the experiment. So one thing I guess I should add is this experiment required a lot of heat. I'm adding it right now. Red triangle up there. Okay. So, hey, if it's a solid, it's removed from the solution, right? That's effectively removing it from the reaction. Solids will not react. You must have stuff dissolved to react it. So that's our two main things. And then a 3 is a prevention. Prevent water from entering the reaction from the atmosphere. Oh, by the way, water in the atmosphere, most of us know that's called humidity, using a drying tube. Here's my lame attempt at artwork again. Piece of glass. It's got a couple notches in it. Notches there to prevent the cotton. There's cotton here. I suppose the cotton's really out here. That's okay. Cotton. And it's going to have beads in there And those are calcium sulfate beads. And they make a hydrate from water too. And this up here on top of the reaction doesn't get hot, so you don't have to worry about the water leaving. So if H2O enters from the air, it gets trapped in the calcium sulfate beads, and it won't enter your flask. Your reaction flask is down there. That's a good little segment on how we use Le Chatelier's principle to get the highest yield of ester we can. And I think we'll stop with that.